Hey, I am a dual degree student and I am pursuing BS Data Science from IIT Madras along with BSc Mathematics from SP College. So, on this channel, I will be covering various topics related to data science as well as mathematics. Let's begin with linear algebra. This playlist will contain these topics. Let's start with vector spaces. So consider a system in n variables which contains m equations. It can be represented using matrices as Ax is equals to B, where A is the matrix of coefficient, x is for variables and B is for constants. So this system can either be consistent or inconsistent. A system is said to be consistent if it has at least one solution. So here there are two cases. Unique solution. So a system can have unique solution if the equations are linearly independent. For example, in this case, these equations intersect at a single point, 1, 0. So they have a unique solution. This is another example. There is another case, infinite solutions. So a system is said to have infinite solutions when the equations are linearly dependent. Here the second equation is a scalar multiple of the first equation, so they are linearly dependent. So here you can see these equations are basically overlapping lines. A system is said to be inconsistent if it doesn't have any solution. So the case is no solution or zero solution. So it occurs when the equations represent parallel lines or parallel planes. Moving further, row echelon form. So it is a structure of matrix which can be obtained using row transformations. So a matrix is said to be in row echelon form if all zeros are at the bottom. The leading entry of each row appears to the right of the leading entry in row above, directly above it, and all entries below the leading entry should be 0 if all the leading entries are 1 and if that one is the only non-zero entry in its column, then it is called as the reduced row echelon form. Now we can find rank and nullity on the basis of row echelon form. Rank is nothing but the number of linearly independent rows. So it is the number of non-zero rows in the row echelon form. Nullity is number of linearly dependent rows. So it is number of 0 rows. We know the basic definition for inverse. It is that the determinant of that matrix should be non-zero, right? So in terms of rank and nullity, if the nullity is 0, that is if it has full rank, then the matrix is said to be invertible. Now consider this example. Here we need to convert A into row echelon form and find and check its invertibility. Now first, 1 is the leading entry of the first row, so all the entries below it should be 0. So we perform R2 minus 4R1 and R3 minus 7R1. We get this. We simplify it by dividing by minus 3 and minus 6 respectively. Then here this one is the leading entry of the second row, so all the entries below it should be 0. So we perform R3 minus R2 and get this. So this is the final row echelon form because it satisfies all the conditions mentioned above. Since it is not in full rank, it is not invertible. There are some other examples which I will not be discussing in depth, but I will be including the link of this PDF so you can go through if you want. Now there is another method of finding rank which is using determinants of submatrices. First we will find the largest possible square submatrix. Then we will calculate its determinant. If the determinant is non-zero, then the rank is equal to the size of the submatrix. But if it is 0, then we will move to smaller submatrix and repeat the process. We will continue until we find a submatrix which will have a non-zero determinant. So for example, we have taken the same matrix for clarity. So here the largest possible submatrix is obviously of 3 by 3, that is the matrix itself. So its determinant is 0, which is not what we want. We want non-zero determinant. So we will consider the first 2 by 2 matrix, which is 1, 2, 4, 5. Its determinant is -3, which is non-zero. Hence the rank is 2, which is exactly what we got using the previous row echelon form method. Now these are some important points. So to find solutions, we can analyze the rank. That is, if we consider the augmented matrix, if the rank of this matrix is not equal to the rank of the original matrix, then the system is inconsistent, that is, it has no solution. But if the ranks are equal, then the system is consistent. Then again there are two cases. The rank is equal to the number of variables, so it has unique solution, and rank is less than the number of variables, so it has infinite solutions. So there are some examples. We will again discuss one. So suppose this system. Now we will get the augmented matrix as this. You can just mention the matrices separately and then get the augmented matrix, but I have just written it directly. Then we will convert it into the row echelon form. Here you can see that the matrix of the augmented the rank of the augmented matrix is equal to the rank of the original matrix, but it is less than the number of variables. Therefore the system has infinite solutions. Similarly, there are various other examples, a lot of examples. Now this type, we will discuss this type of question. I will just explain how we are going to solve it. So to find lambda or mu for each case, we will just find the matrix representation, then find the augmented matrix, convert it into row echelon form, that is reduced it into row echelon form, and then consider the cases, that is rank should be not equal, then rank is equal and equal to number of variables, like that, and find the values of lambda and mu for respective cases. That is the general method for these type of questions. This is the similar question. Now geometric interpretation. So the intersection of the equations in a system which leads to something, right? It leads to a point, it leads to a line or some plane. Okay, so this intersection can be obtained using again echelon form. So we will convert it into an echelon form. We will find the number of possible solutions. So here there are infinite solutions possible since there are two free variables. So this will represent a line which passes through origin. Moving further, field. So these are the important topics of vector spaces. Till now we were just discussing the basics, but now we will go into the actual thing. So field, it is a set of numbers or any other mathematical objects on which addition, subtraction, multiplication or division except by 0 is possible. Similarly to real numbers, the vector spaces are defined over these fields. So there are some properties of fields. First is closure, that is for if there are x and y are two elements in that field or in that set, then their addition and multiplication should be in that set as well. Then commutativity is for any two elements, their addition is commutative, like x plus y is equal to y plus x, and same for multiplication, so xy is equal to yx. Their elements should be associative, that is x plus y plus z should be x plus y plus z, and similar with multiplication. It should follow distributivity, that is x into y plus z is xy plus xz. It should contain unique additive and multiplicative identity elements, that is 0 and 1. So x plus 0 is x and x into 1 is 1. So that's why they are known as identity elements. And inverse, so additive inverse and multiplicative inverse should exist such that x plus minus x is 0 and x into 1 upon x is 1. There are some examples of field like the real numbers, set of real numbers, set of complex numbers, and set of all 2 by 2 matrix, right? 2 by 2 matrices. Now moving further, vector spaces. So V, that is a set, is said to be a vector space over filled K if it satisfies the following conditions. First is closure under addition, then commutativity, associativity, then existence of zero element, additive inverse, scalar product closure, distributivity of vectors, and distributivity for scalars in addition and in multiplication, then existence of 1. So these 10 conditions should be satisfied. We can read them in detail. I will move further and explain them with help of an example. So here the set is R2, that is all the elements of R2 over R1 over the field R. So this shouldn't be R2. This should be this should be R, right? So for all the elements in R2, let x be x, y and z be 3 arbitrary elements of R2 and alpha and beta be 2 scalars from the field R. So to check the conditions, we will just operate the given condition on these arbitrary elements and scalars. So here you can see how I have explained everything, like kind of in detail. We will explain the existence of zero, scalar product closure, etc. Existence of 1. Since all the conditions are satisfied, the given set is a vector space over R. Moving further, this is another example. Now vector subspace. So for a vector space, for any vector space V over a field K, a subset S of V is said to be a vector subspace if it is a vector space itself. Okay. So properties of vector subspace. So it should satisfy the closure under vector addition and closure under scalar multiplication. These two properties are enough to prove that the given space is a vector subspace or not. Given set is a vector subspace or not, sorry. We need to consider this note that every vector space is a subspace of itself and zero set is a subspace of all vector spaces. These are like the standard subspaces. This is an example which we will solve again using the method which we used in vector space. So I won't be discussing this. Then span of vectors. Span is nothing but the results which we obtain by scaling and adding them together, adding two vectors together, right? Two or more. So it is the set of all possible linear combinations of the given vectors. So for example, we need to find span of this. So we will just consider any arbitrary point in R2. Since these belong to R2, right? We will consider any point in R2 and we need to find values of alpha and beta, that is values of some constants, such that we can represent the arbitrary point in terms of these vectors. Right, so any arbitrary point can be represented in the linear combination of the given vectors. So that means that this arbitrary point belongs to the span of these vectors. Right, that means R2 is a subset of S, but we have already seen that the span S is a subset of R2. This only means that if A is a subset of B and B is a subset of A, that means that A is equals to B, right? So S is equal to R square. Therefore, the span is R square. There are some more examples. Now, linear independence. So, suppose there are n vectors in a vector space over a field K. They are said to be linearly independent if the dependence relation is equal to 0, that is alpha 1 u1 plus alpha 2 till alpha n u1 is 0, implies that all the alphas, that is all the constants, are 0. So if all the constants are 0 and then we are getting the dependence relation as 0, then the vectors are linearly independent. But if the dependent relations are 0, dependent relation is 0, but there is at least one constant which is non-zero, then they are linearly dependent. To check if they are linearly independent or not, we will just consider this dependence relation for some constants, and we need to prove it by solving system of linear equation again. Convert it into row echelon form, find the possible solutions. If all the possible solutions for the constants are 0, then they are linearly independent, since here they are non-zero, except when the t is itself 0. These are linearly dependent, and the dependence relation is nothing but just put the values of the constant in place of the alpha 1 and alpha 2. We will get the dependence relation. Moving further, we will see basis, right? So a subset S is said to be a basis of a vector space if the vectors in this set are linearly independent and they span the vector space, right? So to prove that a set, before proving, first just look what is a dimension of a vector space. So we can find dimension of vector space using basis. So the size of the basis is nothing but the dimension of vector space, or the maximum numbers of linearly independent vectors, or the minimum number of spanning vectors. So these three numbers, or these three values, are nothing but the dimension of the vector space. So for example, here, to check if this set is a basis or not, we just have to check if its vectors are linearly independent and if they span the entire vector space. Similarly for various other equations. So these are some questions which I will be discussing. I will be basically telling the general method of solving these questions instead of just going through every single one of them. I'll be back.